And now we're going to move on to Dr. Holz. So I'll hand it off to Kailash, who's our amazing physics competition writer, to introduce.
Thank you, and thank you, Dr. Holz, for coming. Just a little bit about him. Dr. Daniel Holz is a professor of physics at the University of Chicago in the Department of Physics, Department of Astronomy and Astrophysics, Enrico Fermi Institute, and the Kavli Institute for Cosmological Physics, and he pursues research in astrophysics. He's a member of LIGO, the large-scale physics experiment that first successfully detected gravitational waves in 2015 and provided experimental evidence of Einstein's theory of general relativity for the first time in history. Dr. Holz has published over 100 papers on a variety of topics in astrophysics, astronomy, and his work with LIGO, and is here to speak with us today about some of his research, as well as his path to becoming a professor. Thanks for being with us and speaking to help inspire the next generation of scientists and researchers.
Thanks for having me. I'm just sharing my screen. There we go. Okay, so hopefully everyone can see that. Thank you very much for having me. And thanks for that very generous introduction. Let me, I'm just gonna make sure I have a clock here so I don't run out of time. So I was gonna give a short overview. I mean, you've heard a lot of different things already this morning. I'm gonna give an overview of LIGO and some of the interesting results there, just to give you some flavor for what's going on in this field, this brand new field. And then at the end, I'll spend a little time on more general things about at least my path to being a physicist. So to get started, you've already seen this picture from Marcelo. This is the Hubble Deep Field. And I'm talking about something that has occurred a long, long time ago in a galaxy far, far away. Here, there's actually quite technical. It's, on the order of 40 megaparsecs, which is over 100 million light years away. And over 100 million years ago, two neutron stars collided. And the story I'm telling you is about the echoes of this collision and how we got to hear those echoes. So to give you a little background, and I should say, this all happened, what for me is very recent, just a few years ago, after roughly a century of preparation. So here's the basic thing you need to know, and this is at the highest level. The theory we're talking about is general relativity, and it's already been mentioned. Both special and general relativity had already been mentioned. And the basic idea of general relativity, this is our theory of gravity. It's that space and time are linked. And so there's space-time, there's this fabric of space-time, and everything occurs in space-time. And you've probably heard that space-time is warped, like the sun warps space-time, and that's why the Earth goes around the sun. That's how we think about gravity. It's a geometric thing. It's a very powerful idea. But that warping can get stronger and stronger, and eventually, in some sense, become infinite, and that's what we call a black hole. The warping is so strong that light can't escape anymore. Now, something you may be less familiar with is that space-time itself can wiggle. And that's what gravitational waves are. And I'm just going to spend a couple of slides just to give you some intuition for why that happens. I think it's relatively easy to see that there must be something like this. And so here's the picture I want you to have in mind. This is a duck on a pond. And the pond, if the duck is not moving, the surface of the pond is still. Okay? If the duck starts to move, you get ripples in the surface of the pond. Okay. And if you measured those ripples, you could actually figure out, there's a duck. The duck seems to be over there. Here's how fast it's going. You could probably even figure out how big the duck is. There's a lot of information in the pattern of these ripples. The duck, if it moves, generates ripples. There's no way around it. Okay. Gravitational waves are exactly the same thing. You just replace the duck with two neutron stars or two black holes going around each other at close to the speed of light. And then you replace the surface of the pond with space-time itself. And then otherwise, it's pretty much the same thing. As the neutron stars, say, accelerate around each other, they generate ripples in space-time, and those go out to the edges of the universe, and they carry information about what has happened there, how massive those neutron stars are, how fast they're going, where they're located. By measuring the ripples, you can figure out a lot about what's happened. And in fact, those gravitational waves are the way the universe keeps track of where everything is. Whenever anything moves in the universe, it suddenly gets, if you get up and you go to the other side of the room, you emit gravitational waves to tell the entire universe you've moved. Because the whole universe has to know how the gravitational field has changed. Okay, so those are gravitational waves. Now, it took us about 100 years. Einstein first predicted these in 1917. And he thought they would never be detected. Lots of people thought they would never be detected. Even more recently, I think even 20 years ago, you could find people who thought were extremely unlikely to ever detect these. So the question is why? Most people are convinced that gravitational waves exist. Why would it be so hard? And the trick is the scale. And this is one of these things that happens in physics where it's really hard to wrap your mind around what's going on. And you're probably used to, okay, we've talked about how old the universe is, how big it is. These numbers are big. This is another really big or really, really, really super tiny number. And so here's, just to give you again some intuition, when gravitational waves pass through things, they cause the distances to oscillate. So right now, gravitational waves are, whatever room you're in, gravitational waves are passing through and the walls are getting closer and farther apart. But it's by a tiny, minuscule amount. And the relative amount, the fractional amount, is equivalent to, if you look at the distance between us and the nearest star, not the sun, but the next nearest, which is 4 light years away. At the speed of light, it takes you 4 years to get there. Light is pretty speedy, so that's pretty far away. That star is oscillating by the width of a human hair. And we want to measure that. And that's why it's hard. Most people would say, and I think if you think about it, there's this star super far away. It's oscillating back and forth by the width of a human hair. We're going to measure that. If I told you that, you would say, that's insane. It's impossible. It's not going to happen. And a lot of people have said that. The trick is that we built a detector and we actually detected this. And that story is really remarkable. And there's an incredible amount of physics and engineering in that story. I'm not going to spend a lot of time on it. The basic idea is that you shoot photons, just light, down 2 tubes. There are shiny mirrors at the end of the tubes. The light goes out both ends and comes back, and you see which photon gets back first. And you kind of compare that, and that's called a Michelson Interferometer. And if you do that, and it's a very fancy laser and very fancy mirror, there's a lot of very fancy stuff in here, you can actually get to the sensitivity where you detect gravitational waves. Okay, so that's a really fascinating story. I'm going to skip over it just to say we actually built this machine. We actually built 2 of them, and now there are 3, and there'll be a 4th soon. And you can ask more about that later. Okay, so on September 12th, 2015, we first turned on kind of the latest incarnation of these machines, a kind of more sensitive version, the most sensitive version we'd ever had. 2 days later, this is what we heard. And I'm gonna play you the video, and there should be audio as well. So you turn on your, turn up your speakers. This is just a plot where it's just time. And you can think of it as, we detect the wiggling of these mirrors. If you take that and then you just put that signal directly into your speaker and increase the volume by about 20 orders of magnitude, that's what you're going to be hearing directly. And you'll hear it just comes as a thump. I'll play it twice, and then I'll shift it to higher frequency so you can hear it a little clearer. So here we go. So that thump we heard in these two detectors that are very far apart at the same time, and it was actually pretty loud by our, the fact that you can hear it above the noise, that whoosh in the background is just noise. And then suddenly there's this thump in two detectors. That thump, that's black holes colliding. And we analyzed it and we realized it's black holes colliding, and we could figure out all this stuff. And it was incredibly exciting because this was something that had been predicted basically a century before, and we got to hear it. And by analyzing that sound carefully, we figured out it's two black holes. The black holes are crashing into each other at almost the speed of light. Each black hole was 30 times the mass of the sun. So you take our sun, you take 30 of those, and you squash them down into something, 100 kilometers across, something like that. And then you take two of those and you crash them into each other, and it makes this sound that we heard. It's really amazing. And just as an aside, the amount of energy being radiated, the power of these two black holes, it's louder. There's more energy at that moment than all the stars, all the light from all the stars in the entire observable universe combined. Another one of these things that should just blow your mind. Okay, but that was just the beginning. We got a Nobel Prize for that, and it was lots of excitement. But we've continued to operate, and we heard something even more exciting. And so this is to give you some sense of what that was. So what I'm showing here, these are just the drawings of the sounds, if you like. It's just a waveform. This is just time at the bottom, and this is just oscillations. You can think of it as oscillations in a speaker. So it's just the sound. And these are the sounds we've heard. That this green one at the top is the one I just played for you. And that was a thump. It went whoom. That was it. Very short, a fraction of a second. And we've heard some others. At this point, we've actually heard something like 50 of these. I'm just showing a few of them. And some of them are, slightly higher frequency, but they're all kind of basically thumps, and all of these are black holes. Okay. On August 17th, 2017, we heard something very different. Okay, and I'm going to show you that. And so you can see these things here. Now, if you look down at the bottom, I'm now going to show you what we heard on August 17th. Okay, here we go. Now, you can tell this one is a little different. It's going on much, much longer. And it actually goes on much, much longer. The others were thumps. They lasted a fraction of a second. This one lasts over a minute. So I'm not going to have you sit here, but this is a good time to turn up your speakers because this gets really good, I think. So here we go. We're going to jump ahead. And remember, this is what we're hearing in our gravitational wave detector. Okay, so that is what we heard on August 17th. And that is totally different. You can tell just by listening, it's totally different. It's much higher frequency. And that means it's lower mass, because when you go to smaller objects, they can get closer and go around each other faster. And so they merge at higher frequencies. So the farther along you are in this plot, the faster you are when you merge, when the two objects crash into each other. And that means the smaller the mass. And so this is really tiny compared to those 30 solar mass black holes. And in fact, we think these were two neutron stars. Okay, so that's already amazing because that's a whole new class and we got very excited about that. Story doesn't end there. The story continues. Here's another plot. And again, there's some sound here. And so I'm just going to play you. At the bottom is what we heard in our gravitational wave detectors. At the top is what we detected in gamma rays. So very high energy light. There's satellites, including the Fermi satellite, up, orbiting the Earth, and those are observing gamma rays. And here I'm going to play both at the same time, synchronized. that ding is a peak in gamma rays. So these two neutron stars crashed into each other, close to the speed of light. There was a pause of about 2 seconds, and then there was a burst of gamma rays. And that's remarkable. That's called a gamma ray burst. And those happen roughly every day, but some of them have been very mysterious. Now we know, oh, that's coming from two neutron stars crashing into each other. Okay, story doesn't end there. We then pointed a bunch of telescopes and discovered a new star that appeared on the sky. And I don't know if you can see it, there it is. Probably doesn't look that impressive to you, but that's a brand new star. We call it a kilonova. And that was also a result of these two neutron stars crashing into each other. They threw out all this material, very hot material, radioactive material, and it got super bright, and then it dimmed over a few weeks. And we found it on the sky and got to measure the details of that. So this whole story is pretty amazing. Here's a movie. This is an artist's conception. We have a lot of data, but this is kind of to get a close-in view. And the point here is that we're seeing light and we're hearing gravitational waves from the same source. And that's never been done before. And it teaches us all sorts of things. And so I'm just going to talk briefly about some of the things we've learned, and then we'll go from there. Okay. But it's given us profound insights about general relativity, nuclear physics, astrophysics. Tons and tons of papers. Thousands of scientists have gotten excited about this. It's really been one of these transformative events in science. Okay, one thing we learned right away is that, how fast gravity goes compared to light. And so the idea here is, well, you heard that ding from the gamma rays, and then that happened just 2 seconds after the gravitational waves, the merger. And that tells us that light and gravitational waves travel at basically the same speed, because they've been traveling for 100 million years and they arrive within 2 seconds. And in fact, what we think happened was the gamma rays were emitted 2 seconds after the merger, and then they both travel at exactly the same speed. That's a remarkable measurement. It hadn't been done before, and it ruled out a lot of the modified theories. For example, Marcelo mentioned that you can modify gravity, change gravity to try to explain dark matter and dark energy. This means it's much harder to do that, because gravitational waves and light go at the same speed. So there's a whole class of modifications that you can't do. Okay, so that's one thing we learned right away. Another thing we learned by looking at the properties of that star, we figured out that this must be where most of the gold in the universe is made. So, if you have any gold jewelry, any gold around you, that was almost certainly made in binary neutron stars. The collision that we just observed makes 50 times the mass of the Earth in gold and just shoots it out into the universe. So that's been a big mystery. Where is gold made? We helped figure that out. We also got to measure the age of the universe. This is something I'm most excited about, because this is something I'd worked on a long time, wanted to do. And then we had this event and I could do it. I won't go into any details except that we actually got a measurement with this first event. And, it's incredibly exciting. And what's most exciting about it is that as we go on, we'll do even better and better. And this is something people are arguing about a lot in cosmology. It's one of the hot topics in cosmology, and we'll be able to kind of figure some stuff out. Okay, I'm just going to mention as a side, so I'm at the University of Chicago, and I have a group, and here's a recent picture of the group on a social gathering. The angle makes it look like we're close, but we're not. We're all distanced and wearing masks and being very careful. But this is, the group, and we've all worked together for a few years now on all of this science, and it's really been extremely fun. Okay, so I think I have about 5 more minutes, so I'll spend just a little time on some background, since it sounded like you might like to hear a little bit about my path. So I tried to put together some sense of this. My path has been pretty random, to be honest. I have not been super like, oh, I'm going to be a professor and that's all I care about and off I go. I've just, been fascinated by things, as I'm sure all of you are, and just like to ask questions and figure things out. And I had a teacher in high school who was amazing and just encouraged me to keep asking questions. After a while, most people get sick of you asking questions, often because you get to a point where people don't know the answers, and that's frustrating. But he loved it, and he got excited by that, and would just continue to encourage me to ask more questions and go try to figure things out. And so I continued to do that in college and had lots of interests and just pursued them, and kind of had this circuitous route. I went to graduate school, and then I worked at a national laboratory for a while, and then I decided to come and be a professor, and now I'm a professor, and it's great. But mainly just because I get to think about things and continue to ask questions, and that's my full-time job: ask questions and try to figure things out. It's pretty awesome. How do I actually spend my time? I teach classes, undergraduate and graduate classes. I mentor graduate students, so I help them get their PhDs. I spend a lot of my time doing research. You can see some of my papers up here. These are some of the recent things I've been working on. I spend a lot of time talking, going to meetings. We used to be at the board a lot, trying to figure things out. Now it's mostly through Zoom. There's a lot of computer coding. Then I also spend a lot of time, there's other stuff. When you're a professor, you spend time kind of helping run the department and engage in the community. I also, in some of my spare time, I help set the time of the doomsday clock, which is something I really care about, but is a different issue. But I encourage you to learn about that, because it's a group of scientists that are just concerned about the future of civilization. This was founded by Oppenheimer and Einstein shortly after World War II. And unfortunately, these concerns still persist, including climate change and nuclear annihilation. But that's a depressing topic, and so we'll skip that for now. I also spend lots of my time doing other things. Life is really full. Now, I will say just, because I think everyone goes through this, my career path has not been, direct and straight. It's definitely had lots of ups and downs. There are definitely moments where you're like, I'm not sure I'm up to this. I can't figure anything out. I don't know if this path is going to lead anywhere. Maybe I'll go do something else. For a while, I really thought I should go work at Google. There are lots of different things to do. The main thing for me has just been I keep asking questions, because that's what's fun. And things have really worked out. And what's great is you just keep learning from everyone around you, teachers and friends and collaborators, and especially lately students. And it's really been wonderful. I have to say, this path is just, it's so fun. Every day, you just wake up and it's like, what do I want to think about today? And so, yeah, that aspect has really been. So just thinking about this and writing this talk has reminded me, I feel very lucky that way. Anyway, okay, I'll end there.
Wow, thank you so much, Dr. Holz. That was very fun. Does anyone have any questions for him? I actually have a question. As well, you mentioned that before when you were talking about LIGO, that you guys are now making a fourth one, and we could ask about it later.
Yeah. So So what we're doing now is we have two LIGOs. There's one in Hanford, Washington, and Livingston, Louisiana. There's actually a third gravitational wave detector in Italy, outside of Pisa in Italy, called Virgo. And then there are two more new ones being built, one in Japan called Kagra, and one in India called, right now, just LIGO India. And so eventually we hope to have 5 of these detectors. Right now, actually, all of them are being upgraded. LIGO India and Kagra are still being built and refined. The hope is that in about maybe a year and a half or 2 years, we'll turn them all back on, and then we'll start listening again, and we'll see what happens. So there's this whole kind of path forward, and the next decade should be quite fascinating. I should also mention that in addition to the ground-based detectors, there are also plans to put a gravitational wave detector in space. And right now that mission is called LISA, and that's being led mostly by the Europeans, and that would be phenomenal. And that's about a decade away. And that, instead of detecting what they consider tiny black holes, only 30 times the mass of the sun, that one detects million solar mass or more, billion solar mass black holes, the black holes that lurk at the center of galaxies. It detects those crashing into each other, and it can listen to them out to the edge of the universe. So that's a completely different sort of thing with gravitational waves, which would also be phenomenally exciting.
Awesome, thank you. Someone also asked in the chat, does the distance between each gravitational wave increase exponentially as they travel further away from its source, just like in the ponds? And can you use this data to calculate how far away the source is?
Yeah, that's an excellent question. And so, this is just a version of the inverse square law. So, the binary emits energy in gravitational waves, and it's basically the inverse square law says as you get farther and farther away, the amount of energy in the gravitational waves gets less and less. And that's very clearly predicted. And so what it means, and this is specifically when I had that one plot about measuring the age of the universe, that is using this effect by very carefully measuring how loud the gravitational waves are in our detector, we can figure out how far away the binary neutron star was. And that lets us measure the expansion rate of the universe and therefore infer all these profound things. So yes, so energy is conserved, and by utilizing that, we figure out a lot about the universe. Yeah, excellent question.
Awesome. Someone also asked, are there specific locations on Earth better suited to detect these waves? If yes, what characteristics make them better suited?
Yeah, so yes, there are definitely better and worse places to detect these sorts of waves. And it's, these, you can think of it as it's extreme, it's very sensitive, right? We talked about the star at the width of the human hair. It's very sensitive. So you need to be in a place that's extremely quiet. So you can't be near a big city. You can't be geologically active. For example, one of the detectors was put in Livingston, Louisiana, kind of in the middle of nowhere, in the middle of a big forest, which seemed like a good place, except they're logging in that forest, and the trucks driving around and the trees crashing down cause noise, and that's a problem and has to be compensated for. So you try to go to places that are quite isolated and very geologically stable. And so there have been a number of places around the world that have been identified to be, very positive that way. But finding these locations is a big deal because, if it's too loud, all you're going to hear is, traffic on a highway. Or for example, if you're too near the coast, you hear waves crashing on the coast. Where too near is 50 miles or 100 miles, it would be deafening. And so you really have to get away. These detectors are very sensitive. Yeah, good question.
Okay, I think we can take one more question because we have to get moving with our very tight schedule. Mark asks, did the detections from the colliding neutron stars affect our efforts to make a grand unified field theory?
Yeah, okay, so that's a question about, can we unify the forces and understand fundamentally, all of physics? And yes, there are certain things that it gives us clues about, especially if your goal is quantum gravity, where you want to join relativity and quantum mechanics to have one theory which describes everything we've observed in the universe. Right now, as you probably know, there's quantum mechanics, which works extremely well. We just heard a beautiful talk about quantum computing. That all works fine. Then there's general relativity, which describes cosmology, black holes, all the big stuff. That works totally fine. But we know the theories don't play well together, and we need a theory that kind of fixes that and does it all. And so that's something we're looking for. Needless to say, here's a case where we have quantum mechanics. The light is being generated by quantum mechanical processes, and relativity, general relativity, gravity, which is generating the gravitational waves. So it's a natural place where we get to combine that. And so I gave you the example of the speed of light. Just knowing that gravitational waves, gravitons, if you like, travel at the speed of light, that they're the same, is a major advance. One of the things I looked at, I thought was just super fun, was you could also use this to figure out the number of dimensions in the universe. And so just by taking this binary neutron star, we figured out that the universe has 3 + 1 space-time dimensions, 3 spatial dimensions and 1 time dimension. Now you're probably thinking, you just look around your room, you can tell there are only 3 dimensions plus time. But we use this system to determine that the universe, that's true out to 100 million light years away. That even on cosmological distances, there are still only 3 + 1 space-time dimensions. And that's, very, very interesting. And we used it by comparing how loud the gravitational waves were to properties of the light. So yeah, we're learning an incredible amount about physics, basic fundamental physics from these sorts of detections. And I should say this is just the first one. We hope to do many, many more. And so there's a lot still to learn. Great question.
Awesome. Thank you so much, Dr. Holz. I hope everyone enjoyed that talk and all of the previous physics talks. I certainly have.